treaties, environmental treaties. I'm going to do 4 things. Well, actually 5. I'm going to start with your basic provision of a public good. I'll be brief there. I'll talk about cartel formation a bit more extensively. Then I'm going to talk about the international climate negotiations. Talk about acidification, talk about the hole in the ozone layer, and then tie it all back to climate at the end. And I'm going to take 2 hours for that. Last week I talked about optimal climate policy. And we found that if you want to maximize welfare, then you should equate marginal cost to marginal benefits in a dynamic problem like climate change. You should equate the marginal cost of emission reduction to the net present value of the flow of marginal benefits of emission reduction. And if you do that graphically, then what you would find is that almost always you would go for an interior solution. You would avoid at a corner of no emissions control, and you would also avoid the corner of 100% emission control. The optimum lies somewhere in between. I showed you this graph, which essentially has the required carbon tax as a function of the goal, the long-term goal of climate policy, or vice versa, for a particular carbon tax. What is the long-term atmospheric concentration of greenhouse gases that you could expect? We talked about the willingness to pay for greenhouse gas emission reduction. It's around a price for carbon, the amount of tax that we would want to apply. And if you put the two together, what you would find is that if you want to maximize welfare, then we would reduce greenhouse gas emissions, but nowhere near enough to stabilize the concentration of CO2 in the atmosphere, and definitely not in the present century. So that's all what we've done. Now, what we're going to do today is essentially move away from the rather tall assumption that there is a global benevolent dictator or global social planner. We're going to move to the situation where there is actually still a pretty old assumption. There are many such planners governing all rather than they fully coordinate. Now, what you're looking at here is a result from these 2 gentlemen, Bill Nordhaus and Zilin Yang. Nordhaus is at Yale, Yang is University of New York, I think in Buffalo. But don't hold me to that. Definitely somewhere in New York. And what we have here is the optimal concentration of CO2 in the atmosphere. Here we have time. And then we're looking at 4 different scenarios. The top one is without emission control. The bottom one is the one we looked at previously. That is what the DICE model says, that assumes that the world in one whole. And then here, and that's the relevant thing for today, we're looking at 2 different scenarios. One in which all countries cooperate to jointly reduce their greenhouse gas emissions, and the other where every country only optimizes its own welfare, disregarding the impacts of climate change that it would impose through its emissions on the rest of the world. And lo and behold, what we find is that in the non-cooperative equilibrium, where everybody plays NAS, we find less emission reduction than in the cooperative. Remember, the difference between DICE and full cooperation is way beyond us at the moment. So why is this difference? Well, essentially what you do in cost-benefit analysis is you equate the marginal cost to the marginal benefits. And the marginal benefits in global cooperation are the marginal benefits of greenhouse gas emission reduction for the world as a whole. That's the circle. If you go for private maximization, you're only interested in maximizing your own welfare, then you would still equate the marginal cost to the marginal benefits. Marginal costs haven't changed, but the marginal benefits are now that share of the impacts at the margin that fall in your own country, which is necessarily a fraction of the global. In this particular scenario, the global PGU tax would be $23 per ton of carbon, but the European PGU tax would only be 4% of that. That's $8 and a bit. So that explains why, if cooperation falls apart, we move from this scenario, which does a bit of emission reduction, to this scenario, which still does emission reduction, because it's not that the problem has completely disappeared, it's just that you care only about a small fraction of the problem. So this is exactly what you would expect from standard game theory. We would expect countries to not cooperate, and that is because of this property called Freeriding. I think it's best understood in a numerical example. You've seen bits of this in micro already, so we can probably be fairly quick here. So let's assume that the costs of emission reduction for country I are C sub I, and that's a quadratic function in their emission reduction R. So essentially costs accelerate as you get more ambitious. And for sanity's sake, we assume that the cost of emission reduction of country I are independent of what other countries are doing. The benefits of emission reduction are given by B sub I, which is a linear function of all emission reductions in all countries. So essentially we sum over what everybody else is doing, and R here should be interpreted as relative emission reduction, so we should weigh that by their amount of emissions E, right? That's essentially the importance. This is the importance of other countries, and this is how much they do. And then the beta is how much you care about climate change. Non-cooperative solution is very simple. For every I, what we have is that we want to equate the marginal cost to the marginal benefits, marginal cost of 2 alpha R. The marginal benefits are the first partial derivative of this thing to R sub I. Rj is independent of Ri for all j's that are not equal to I. So all those terms become 0. And Ri times Ei derived to Ri is of course just E. So that is what pops up here, and then of course you have to multiply that with the beta. So this is our first order condition for optimality. We can work this out and find that the optimal amount of emission reduction for country I, this should be a subscript here, is beta I Ei over 2 alpha I, and that holds for all countries. So that is what you would do if you would ignore your impact on the rest of the world. the cooperative solution, you want to maximize the sum of all costs minus the sum of all benefits, but the sum of all costs, the first partial derivative of that to R is pretty simple because there's no, or at least by assumption, there's no dependence in emission reduction between the countries. So that just stays the same, right? dCdr is 2 alpha R. But we want to take the sum of all benefits to and derive that to Ri. And what happens then is that the thing that pops up is your emissions, which is your influence on the problem, times the sum of all the betas. So this is essentially the intensity of concern summed for all countries. So we want to take the first partial derivative of this thing to Ri, right? So that pops up everywhere. But then, because we're summing over the betas for all countries, we have a double sum, essentially. And then that implies that your emissions EI pop up in combination with all the other betas, right? So what we have is that optimal emission reduction for all countries I in the cooperative solution is beta E over 2 alpha. Which looks very similar to the non-cooperative solution. Well, went the wrong way. Which was also beta over 2 alpha, beta E over 2 alpha, but the main difference is that the subscript is dropped from the beta. The beta is now the sum over all betas. Now, what is free riding? Free riding is actually a very strange concept. The starting point is the situation in which all countries play nice, everybody cooperates with everybody, and we're jointly maximizing our welfare. And then the question you ask is, what would happen if I stop cooperating, but all the others continue to cooperate? That is essentially the question you're asking when you're considering to free ride on the grand coalition. And the crucial assumption there is that you assume that the others continue to play cooperatively. So what is the difference in costs? Essentially C prime minus C star, right? So in C prime, we have that emission reduction is R prime, so we stick that in the cost function, so we have beta squared. E squared over 4 alpha I. In the non-cooperative, in very similar structure, but we have the subscript pops up again in the beta. So we'll work this out. So this is really the difference between the beta and the beta I, both squared, and then times this constant. The difference in benefits is where the somewhat peculiar assumption of free riding comes in. Namely, you assume that all the others continue to play cooperatively. So the only difference is the difference in your emissions. So the difference in benefits, beta minus beta double prime, not beta star, is that you reduce your emissions, but the rest continues to play. So the only difference is in your emissions, so that's Ri minus R star, times, of course, your level of concern, times your emissions. So that works out to beta I times beta minus beta I over this, and then times this constant here, where the difference between these two is a factor 2, right? EI squared pops up, alpha I pops up, in both. So really, this is factor 1/2 difference. So this immediately shows that it almost always pays to free ride, right? It just follows from this thing against this thing. You can do that formally. You can also just plug in some numbers and see what happens. So here I just play these two equations back. Let's assume that alpha is 1/2, right? So this is 1. Let's assume that E is 1. So essentially what we have here is 1, what we have here is 1/2, right? So that just makes it easy. And let's assume that beta, the sum over all marginal impacts in the whole world, is 4, whereas beta I is 1. Essentially what we assume here is that the country that is considering to free ride, country I, is 1/4 of the world's problems, right? So we stick that in here. So that's 4 squared minus 1 squared is 15, over 2 is 7.5. 4 minus 1 is 3, times 1 is still 3, times 1 is still 3. So the cost savings from free riding are 7.5, and the additional impacts of climate change, the lost benefits, the foregone benefits of emission reduction, are only 3. So under these assumptions, if you're 1/4 of the world's problems, then it pays off to free ride. The cost savings of free riding are greater than the additional impacts. Let's assume that country I is only 1/10 of the problem rather than 1/4. So we have 10 squared minus 1, 99 over half is 49. 99 over 2 is 49.5. 10 minus 1 times 1 times 1 is 9. So if a country is a smaller part of the globe, since the world becomes larger relative to yourself, then the gap between the costs and the benefits actually increases. Compare this scenario to this scenario, essentially what we find is that smaller countries have a greater incentive to free ride than do larger countries. Now what happens if we're 1/2 of the world? 2 squared minus 1 over 2 is 3 divided by 2 is 1.5. 2 minus 1 times 1 times 1 is 1. So even if half the damages fall on yourself, then it still makes sense to free ride. So it is in everybody's best interest to leave the Grand Coalition, and as a result, cooperation falls apart. And we move to the situation where everybody only plays nice, right? So instead of optimizing like this, everybody optimizes like this. That is, they only heed the impacts of climate change that fall on their own jurisdiction. That's a central prediction of game theory. It's a provision of public goods. It's a commons game, essentially. Everybody walks away from full cooperation. I must admit that I don't quite know how old this theorem is. Definitely it was part of John Ness's work. It has been reaffirmed later on. And I think it actually, as a central prediction, predates Ness. And it was sort of first found to apply to climate change as well without a major surprise in a paper by Pereira, OEC Skalko in 1992. Freeriding makes a very simple assumption, right? There's two situations. In one situation, everybody cooperates. We find that that is not rational for the individual players. And in the other situation, nobody cooperates. And you may wonder, is there a situation in between? Where some people cooperate or some countries cooperate with one another, but the rest of the world does not cooperate at all. It's a logical question to ask, and it has been answered. And most of the literature that looks at this applies so-called cartel theory that was developed by Claude Daspermont of the Université Catholique de Louvain. And as you may have guessed, cartel theory comes out of industrial organization, and essentially the question in cartel theory is, do companies in a market have incentives, and would they be able to form a cartel, and would that cartel survive market forces? But the concepts of cartel theory actually carry over to international environmental agreements without too much bother. The basic idea of cartel theory is so-called coalitional stability, and a coalition is said to be stable. A coalition is essentially a group, in this case countries, that come together to jointly maximize their welfare. And a coalition is said to be stable if and only if it's profitable. That is, everybody in the coalition is better off than they would be in the net equilibrium, where nobody cooperates, everybody's purely selfish. A coalition is said to be stable if and only if it is internally stable. That is, no member of the coalition is better off by leaving the coalition. And a coalition is said to be stable if and only if it is externally stable. Then there's no non-member of the coalition would be better off by joining the coalition. To get a bit more intuition behind it, if everybody cooperates, then there's nobody outside who would want to join, so the grand coalition is by definition externally stable. And if the coalition consists of two players, then profitability and internal stability are the same, right? Because if there's two players, one leaves, then you're back to the situation of full non-cooperation. But of course, if there's three players in the coalition, then there's a difference between one player leaving and two continuing to cooperate, internal stability, and the coalition of three players falling apart into three atoms, into three non-cooperative players. So if you have three or more players in the coalition, then internal stability and profitability are no longer the same condition, right? So this is essentially just a set of definitions, right? A coalition or a cartel is stable if it's profitable, internally stable, and externally stable. I find these things easiest to understand if you just work through some equations. That essentially will tell you what happens, right? So let's assume that we have just two countries, 1 and 2. The cost functions are still quadratic as they were before. Benefits of emission reduction are also the same as before, but I've replaced the summation sign with R1E1 plus R2E2, right? This is just a summation sign, but because we have two entries in the summation only, we might as well work. And the same for B2. Non-cooperative solution, you don't care about the costs of the other or the benefits of the other, so you simply set your marginal cost equal to your marginal benefits, 2 alpha R equals beta E. So your optimal emission reduction is as it was before, beta 1 times E1 over 2 alpha 1, and the same holds for the other country. But of course the indices are now of 2, right? Cooperative solution is essentially you take the sum of the costs of both countries, but the costs of the other country then does not depend by assumption on what you're doing yourself. So that just stays 2 alpha R1. But now, of course, the sum of the benefits, your emissions pop up in the welfare function or the payer function of the other. So we take the sum. Of the two betas, and essentially what we have is a cooperative emission reduction. Sum of the betas times E1 of 2 alpha, and the same goes for the other. Nothing has changed, except that rather than having I countries, we now have 2 countries, so the equations are all just a bit less messy. So what happens here essentially, R1 prime is beta 1 plus beta 2 times E over 2 alpha in the cooperative solution. In the non-cooperative solution, R1 is beta times E1 over 2 alpha. So the difference between this expression and this expression is beta 2, right? So what happens, well, times E1 over 2 alpha 1. So what happens is that you increase your emission reduction by this amount. That's essentially how much damage you do to the other at the margin. Over the amounts that would maximize your own welfare. Now that is a bit of a painful thing to do, right? You do more than you would do than what is in your own self-interest. But player 2 responds, and player 2 increases emission reduction as well by the amount of beta 1. Right? So that is what coalition formation does here. This is what cooperation does. Player 1 reduces her emissions, and in return, player 2 reduces his emissions. Right? We can work out the difference in costs. Same expression as we had before. It's beta 1 times it's beta 2. I actually think that this is wrong. I haven't worked it out fully. Yeah, this is beta 1. No, this is correct. It's beta 1 times beta 2 plus beta 2 squared. Difference in benefits, same story again. That's beta 1 and then times the difference, beta 2, beta 1. So the difference between these two is as before, is that there's a square missing, right? Essentially, the way this works intuitively is, I mean, the conditions for coalition stability are that it's profitable, right? That you don't want to leave profitable and internally stable. We're looking at two players only, so the two are the same. So essentially what you're saying is that by joining the coalition, I would want to see an improvement in my welfare relative to the situation where there's no improvement. There's a change in both costs and benefits. So what you want as player one is that the increase in benefits exceeds the increase in costs. Now, when is that condition met? What does cooperation do? You increase your emission reduction. So that brings an additional cost. So what you want to do is keep this thing small, right? So you want to increase your emission reduction by a little bit. You want to reduce your emissions by a little bit more than you would in the non-cooperative case. But at the same time, so you want to keep this thing small, but you want to make this thing large. You would hope that in return to you increasing your effort by a little bit, the other player will increase his effort by a lot. And that creates a large delta B. So that is what you would hope to get out of the coalition. Now the other player has the exact same considerations. So he would hope to increase his effort by a little, and in response he would hope that you would increase your efforts by a lot. Right? So that his delta C is small, but his delta B is large. So that is what you hope to get out of coalition formation. You do a little bit more, the other does a lot more. But of course the other isn't crazy and hopes the exact same from you. He will do a little bit more and you will do a lot more. And in order for the coalition to be stable, in order for the coalition to be profitable to both players, not just to you, both conditions have to be met simultaneously. Essentially, you can draw this up as an Edwards box. It's essentially barter, a barter economy, right? And if you phrase it like this, it's pretty obvious that a coalition is not going to do a lot more than playing non-cooperatively, right? Now, this was pointed out by these two gentlemen, Paulo Carraro and Scott Barrett, in the early 90s. And essentially, Carraro said if you apply this sort of cartel formation theory, then nothing much will happen. Scott Barrett refined it a little bit in a paper in 1994. And the way I told the story is essentially because there's so many conditions being imposed on the coalition. And if you go to 3 players, and essentially we would have that for player number 3, also the increase in costs would be small, whereas the increase in benefits would expect to be large. And if you add 4th player, you would add yet another condition to the stability of the coalition, right? You just keep going there. Essentially what Carraro showed is that the number of players in any coalition, the number of cooperative countries would be fairly small. Barrett showed that there's actually a second solution to this, and it is that everybody who is in the coalition, and there can be a large amount of people in the coalition, if they do almost the same as they would do in a fully non-cooperative solution. So Barrett predicted that the coalition is either small but deep. Small in the sense that there's a few players, deep in the sense that they do a lot more than they would have done on the nest, or the coalition is large but shallow. Large in the sense that a lot of countries would play cooperatively, but shallow in the sense that they won't do a lot more than they would do on the nest. So that is the basic prediction of the two basic predictions of game theory, right? Countries would seek to free ride, and even if you allow for smaller coalitions and the grand coalitions, then nothing much in addition would happen. It's a basic prediction was made in the early 90s. People have tried to overturn it, but hasn't really worked. So how do these predictions stand up to reality? So what I'm going to do over the next hour or so, I'm going to make a small start and then I'm going to finish this afternoon. What has happened in the international climate negotiations? Basic notion that if you put more CO2 in the atmosphere, then the world will get warmer, was put on the scientific agenda by Svante Arrhenius in 1896. This is no news at all. But nobody took this too seriously in the sense that they drew policy consequences from it or actively researched this until the early 1980s, and politicians only started paying attention in the late 1980s, following two international conferences in 85 and 86, and actually it was Lady Thatcher, then Prime Minister of the UK, who was the first senior politician to embrace climate policy. Things moved pretty fast from then on. So in 85, the first international conference, 86, the second international conference, 88, a preparatory conference in Noordwijk. First two were in Austria, and then in 1992 there was a major conference on environment and development. The second one in Rio de Janeiro. The first one was in 72 in Stockholm. The Rio conference did a number of things. 5 major international treaties were negotiated, 4 of which have been forgotten. But the 5th one lives on, and it's called the United Nations Framework Convention on Climate Change, negotiated in 1992. We've met it before. It has been ratified by basically all countries, apart from a few rogue ones like North Korea and the Vatican. One of the reasons that it was so popular and ratified so quickly is essentially because it doesn't do a whole lot. The UNFCCC is a framework convention. It essentially sets the rules for international negotiations rather than that it sets the outcome. And of course, agreeing on talking to each other is something that diplomats quite like, right? Because it's lots of international travel that comes with it. Not a whole lot was promised, except for 2 things. There's only 2 substantial matters in the UNFCCC. One is a major headache, that is that it speaks of common but differentiated responsibilities. The common responsibility is essentially saying this is a global public good. It's a shared problem of humankind. Which is a rather trivial statement to make if it comes to climate change. But it also says differentiated responsibilities, which essentially means, which is climate speak for saying It's the rich countries that done it, and therefore they must take the lead in solving it. Even though it's a problem that primarily falls on poor countries, and therefore they have the greatest interest in solving this problem, the climate negotiations say that rich countries should take the lead. And the second thing, and we've been there last week, is that the UNFCCC says that the atmospheric concentration of greenhouse gases in the atmosphere should be stabilized at an undefined level, but stabilized. So essentially, those are the two substantial things that the UNFCCC did, and all the rest is essentially it promises international negotiations. And international negotiations there have been. The treaty was negotiated in 1992. It sort of entered into force in 1995. In the beginning, the UNFCCC essentially says there shall be at least one meeting per year. And in the beginning, there was about one meeting per year. By now, and actually I should update this to the last 2 years, by now there's actually at least 2 meetings a week under the UNFCCC. So there's the major conference that's typically late November, early December. And this year it will be Paris, last year it was Lima. First one was in Berlin. It's typically a 2-week conference where about 40,000 people attend. They decided that that is not enough, so a while ago they introduced a preparatory meeting half a year before. They said that's not enough. So now there's 4 major gatherings every 3 months where a large amount of negotiators gather. And what they do in these meetings is that they create committees and subgroups and needs for training and needs for assessment, and they then sort of create their own momentum and their own series of meetings. So that by now we are down to 2 meetings a week on the international climate negotiations. So that is the blue curve you see. So in that sense, the UNFCCC has also been a resounding success, right? The aim was to create international negotiations, and we've seen lots of people gathering in rooms, talking to each other. The annual costs of these things, and this is just the salaries of the people attending and the travel costs and the hotels and stuff, not the costs of the back offices back home, has gone up to say $130 million per year on the international circus alone. So, this afternoon I'm going to talk about what actually happened during those meetings in terms of substance. Okay, we'll see you guys then.